Hello everyone, hello students. I hope you are doing very well. So I am Brijesh Kumar and today we are going to start day 25 of our JEE 45 days crash course. Okay, so let's begin with the session. So in this today's session we are going to cover P block elements group 15 to group 18. That means group 15, group 16, group 17 and group 18. This is the syllabus for JEE-Main 2024. Okay, group 13 to group 18 you can see. Now you can see the approx weightage 2-3 questions, okay, in past JEE exams you can see. Let's discuss the today's topic, which is group 15 to group 18 elements. So let's begin with the session. What are the topics to be covered today? Let's quickly see these and then we will discuss. So group 15 elements, that means nitrogen family. In this today's session we are going to discuss nitrogen family. Then we will discuss chemical and physical trends of the group 15 elements, that means nitrogen family. Then we will discuss important reactions of the group 15 elements, that means nitrogen family. Then we will discuss group 16 elements, oxygen family. Same chemical and physical trends of the group 16 elements, oxygen family. And then important reactions of the group 16 elements, oxygen family. Similar pattern we will follow for group 17 elements, halogens, chemical and physical trends of the group 17 elements, then important reactions of the group 17 elements. Then group 18 elements, noble gases, inert gases, chemical and physical trends of the group 18 elements, noble gases, and important reactions of the group 18 elements. Now you can see the periodic table. As you know very well, in this periodic table 118 elements are there, and out of these 118 elements you can see this box. This box includes the P block elements. Okay, this is the group 13 elements, boron family. This is the group 14, which one, carbon family. This is nitrogen family, group 15. This is oxygen family, group 16. This is fluorine family, group 17, and this is halogens, right? Fluorine family, that means you can say fluorine family, that means you can say halogens. And this one, last one, is group 18, which is noble gases. Okay, so yesterday we have covered group 13 and group 14, and today we are going to cover 15, 16, 17 and 18 group, these four groups. Okay, so be ready and let's begin with the session. So this is the periodic table, and first of all I want to give a roughly idea about the general electronic configuration of P block. So the general electronic configuration of P block is NH2NP126, as you know very well. NH2NP126. So NH2NP14, NP1, NH2 is fixed. Then for group 14 NP2, for group 15 NP3, for group 16 NP4, for group 17 NP5, and for group 18 NP6. Okay, so this is the general electronic configuration. So let's see the electronic configuration of group 15 elements. You can see in group 15 we have nitrogen, phosphorus, arsenic, antimony and bismuth, and the last element is radioactive element, so we are not going to discuss that. Okay, we are discussing only these five elements. So you can see atomic number of nitrogen is 7, electronic configuration is 1s2, 2s2, 2p3. So you can see ns2 np3, right? In each case you will find S2P3, S2P3, S2P3. Only the period number is changing. That means only the valence shell is changing. Second to third, third to fourth, fourth to fifth, fifth to sixth. Okay. Phosphorus atomic number is 15. Arsenic atomic number is 33. Antimony, that means symbol is SB. Atomic number is 51, and bismuth atomic number is 83. You can see the last shell electronic configuration for each element of group 15. You can see 3s2 3p3. You can see 4s2 3p3. 5s2 5p3, 4s2 4p3. Okay, and you can see 6s2 6p3. That means the general electronic configuration is ns2np3, ns2np3. So that is the electronic configuration of group 15 elements. Let's discuss the group 15 elements nitrogen family, right? Okay, so let's begin with the chemical properties. So we are going to discuss chemical properties, then we will discuss physical trends. So chemical properties, you know very well the electronic configuration, the general electronic configuration of group 15 elements is ns2np3. What is ns2np3? Okay, okay, so the oxidation state, the general oxidation states are -3, +3 and +5. -3, +3 and +5. So what it can do, it can accept 3 electrons. Okay, it can accept 3 electrons to complete its octet. Okay, that means it will show -3 oxidation state, it can show +3 oxidation state, it can lose 3 electrons, and it can lose all 5 electrons, all 5 valence electrons which are present in ns and np. Okay, That's about the oxidation state, -3, +3 and +5. Reactivity: nitrogen is relatively unreactive, right? N2 gas is, N2 gas is unreactive, right? Similarly, nitrogen is relatively unreactive, while other elements in the family show increasing reactivity downwards. If you are moving in a periodic table, you can see this is the periodic table, right? This is the periodic table. Suppose this is group 15, nitrogen, phosphorus, arsenic, antimony and bismuth, right? We are not discussing radioactive elements. So if you are moving top to bottom in a particular group, so reactivity will increase, and nitrogen is relatively unreactive. Let's discuss the another point: electronegativity, ionization energy and atomic radius. Okay, we are discussing what? We are discussing chemical properties, and in chemical properties we have discussed electronic configuration, oxidation state and reactivity. Now let's discuss electronegativity, ionization energy and atomic radius. What is electronegativity? You know very well, electronegativity is nothing that is a tendency to attract the shared pair of electron toward itself. If we are moving left to right across a period, what happens? Atomic size decreases. If atomic size decreases, Z effective will increase. If Z effective will increase, definitely electronegativity will increase, right? Okay, and top to bottom, due to the addition of new shell, the major factor is due to the addition of new shell, electronegativity will decrease. What? Due to the addition of new shell, atomic size increase, Z effective decrease and electronegativity also decrease. So what you can say in this periodic table, if you are moving left to right, electronegativity will increase. If you are moving left to right, electronegativity will increase, and if you are moving top to bottom, electronegativity will decrease. Okay, that's a very interesting point. So electronegativity decreases down the group, top to bottom in a periodic table. What is ionization energy? You know very well, that is the amount of energy required to remove an electron from its outermost shell of an isolated gaseous atom. That is the point, right? If size is large and its size is small, right? As I told you already, you can see here, suppose the size is only this and this is the last shell and electron is here, and suppose this is the nucleus and size is like this, and here is the electron. So this distance is more here, that means the attraction is less. The nucleus hold towards this electron is less. If nucleus hold towards this electron is less, that means the electrostatic force of attractions are less in this case, right, between the nucleus and outermost shell electrons. So what happens? It requires less amount of energy, right, to remove this electron, and this one distance is less, so it requires more amount of energy to remove this electron. So ionization enthalpy decreases with size, right? So as we are moving top to bottom, size increases, so definitely ionization enthalpy decreases. But if you are moving left to as you are moving top to bottom in a particular group, okay, listen me very carefully, I am repeating my points. As you are moving left to right, okay, across a period, so size decrease. If size decrease, ionization enthalpy increase. Okay, ionization enthalpy increase. If you are moving top to bottom, size increase, ionization enthalpy decrease, because if size is more, it requires less amount of energy to remove that particular outermost shell electron, right? That is the point here. I hope you are getting this point. So size, like the ionization energy or ionization enthalpy is inversely related to size, you can say. If ionization enthalpy is more, size is less, right? You can say if size is more, ionization enthalpy will be less. If size is less, ionization enthalpy will be more. Okay, so you can see here it decreases down the group. And atomic radius, as I told you already, if you are moving left to right across a period, so what happens? Atomic size decreases, right? Atomic size decreases, so atomic radius decreases and Z effective increases. But if you are moving top to bottom, due to the addition of new cell, atomic radius increases. That means atomic size increases down the group. Okay, and ionization energy decreases down the group because atomic size increases. Okay, that's all about the some properties. Let's discuss the physical trends. Now you can see atomic size increases. Atomic size increases down the group, as I told you already. Melting and boiling point increases down the group, because if atomic size increases and the size becomes larger, so the interaction part will increase, right? So the interaction part increases, as well as if atomic mass increases, so definitely what happens? Melting point and boiling point will increase. Okay, density increases down the group. Density formula is mass by volume. If mass will increase, so definitely density will increase, right? So that's the point point. Okay, let's discuss the next, electronegativity and ionization energy. Electronegativity decreases down the group and ionization energy decreases down the group. So we have discussed these points. Electronegativity increases left to right across a period, and electronegativity will decrease down the group top to bottom. Okay, top to bottom it will decrease and left to right it will increase. But ionization energy left to right will increase because size decrease, and ionization energy top to bottom decreases because size increases. Okay, let's discuss some chemical reactions. You can see reaction with oxygen, hydrogen and halogens. The first reaction is reaction with oxygen. It forms oxides like nitrogen oxide. You can see dinitrogen oxide, N2O. Like you can see NO. N2O is also named as laughing gas. Okay, NO nitric oxide or nitrogen monoxide. You can see N2O3 dinitrogen trioxide. You can see N2O4, N2O5. You can see the oxidation state. In this case N2O it is +1, right? Because 2x minus 2 equal to 0, you have to calculate like this. So x comes out to be +1, right? In this case NO, you can see the oxidation state will be, similarly you can calculate in the case of NO. Similarly N2O3, N2O4 and N2O5. Reaction with hydrogen, it forms hydrides. With oxygen it forms oxides. With the hydrogen it forms hydrides. Example you can see like ammonia, which is nitrogen hydride, NH3. Like PS3, phosphine, it is named as phosphine, right? Like SBH3, like this. Okay, like SBH3 it is named as stibethene. Okay, so this is all about NH3, PS3, SBH3. I hope you are very much clear about this. Let's move to the next point, reaction with halogens. It forms halides. Halides, that means reaction with halogens, it will form NF3, it will form PF3. Okay, so it will form like SbCl5, it will form SbCl like 3. Okay, let's discuss the next point, reaction with metals and acids. So reaction with metals, it forms metal nitrides, for example Li3N and Mg3N2. When lithium reacts with what, nitrogen, it will form lithium nitride, right? Nitride means nitrogen is in 3 negative. Okay, and similarly Mg3N2 magnesium nitride. Reaction with acids, it forms ammonium salts. Okay, like NH4Cl ammonium chloride, like NH4NO3 ammonium nitrate, like NH4SO4 ammonium sulfate, like this, etc. Okay, so NH4SO4, is it correct? No. If you have to write NH4 whole twice SO4. Okay, balancing charges is must. Okay, so NH4 whole twice SO4. Let's move to the next point. Let's discuss in detail reaction of nitrogen. So combustion reaction. First reaction is combustion reaction. Combustion reaction, that means in presence of oxygen, in presence of oxygen. So N2, in presence of oxygen it will form nitric oxide, that means nitrogen monoxide. N2 plus O2 gives 2NO. Reaction with hydrogen, so N2 plus 3H2 gives 2NH3. So this reaction is named as Haber's process. Okay, reaction with metals, 3N2 plus 5M, it will give 2M3N2, where M is a metal. M is what? M is a metal. So these are the reaction with metals, combustion reaction and reaction with hydrogen. Next, similarly, reaction of phosphorus, you can see reaction with oxygen. So P4 when react with oxygen, it will form, so P4 plus 5O2 gives P4O10. P4 plus 5O2 gives P4O10, and the simplest one will be P2O5 as well, right? So it is like a dimer. Okay, next one is reaction with hydrogen. P4 plus 6H2 gives 4PS3. So 4 molecules of PS3 means phosphine. Okay, next one is reaction with metals. So 3P plus 5M gives a 3MP, where M is in nothing, M is a metal. Next, reaction of arsenic. So same reaction with oxygen. So 2As plus 3O2. So whenever nitrogen, phosphorus, arsenic, they are reacting with oxygen, they will form their oxides, their respective oxides. So 2As plus 3O2 gives 2As2O3 arsenic oxide. Similarly, reaction with hydrogen, they will form their respective hydride. So As2 plus 6H2. As2 plus 6H2 gives 2AsH3. Reaction with metals, As plus 3M gives MAs, where M is a what? M is a metal. So let's move to the next point, reaction with reaction of antimony. Antimony symbol is Sb. First reaction is reaction with oxygen. So 2Sb plus 3O2 gives 2Sb2O3. Same what? Antimony oxide. Next reaction with hydrogen Sb2 plus 6H2 gives 2SbH3. This is balanced chemical equation. Okay, you can see. Reaction with metals Sb plus 3m gives Msb. Okay, Sb plus 3m gives Msb. Now let's move to the reaction of bismuth. So reaction with oxygens 4Bi plus 3O2 gives 2Bi2O3. Reaction with hydrogen gives BiH3, that means Bi2 plus 6H2 gives 2BiH3. Next one is reaction with metals. So Bi plus M gives Mbi, right? Okay, let's move to the next. Important reactions of the group 15 elements nitrogen family. The first one is ammonia, NS3. So how can we form ammonia? That is the point. So you know Haber's process. Haber's process, right? As I told you already, this is the Haber's process for the formation of ammonia. So N2 gas plus 3H2 gas, right? This is the sign of equilibrium. This is the sign of equilibrium. Okay, N2 gas plus 3H2 gas gives ammonia, which is 2NH3, right? Same reaction with acids. You can see ammonia when react with acids, it will form ammonium halide, right? If X is a what? Halogen. For example, you can see here NH3 plus HCl, it will form NH4 positive and Cl negative. So what is happened here? So you can see here ammonia has lone pairs, hydrogen will be positive, Cl will be negative, ammonia will accept this hydrogen because acids means loss of proton, acids means loss of hydrogen, H positive, right? Next is reaction with copper 2 oxide. Copper 2 oxide means what? CuO. CuO. Okay, copper 2 oxide means CuO, and copper 1 oxide means Cu2O. Cu2O means copper 1 oxide. Okay, so 2NH3 plus 3CuO, it will provide 3Cu plus 3H2 plus N2. So you can see nitrogen oxidation state is 0 here, and here nitrogen oxidation state is what? Tell me. Here nitrogen oxidation state is plus 3. Here nitrogen oxidation state is plus 3 because hydrogen is present as hydride. That means hydrogen is present as H negative. So nitrogen oxidation state will be X. You can consider this X minus 3 equal to 0. X comes out to be plus 3. So plus 3 to 0, that means reduction. That means reduction, right? Plus 3 to 0. Plus 3 to 0 means reduction. Okay. Similarly, copper. Copper is here in plus 2 oxidation state, plus 2 to 0, like this. So you can understand it very clearly. I hope this is clear. Let's move to the next point. So these are hydrides. These are hydrides of nitrogen. The next point is reaction with excess of chlorine gas. Excess of chlorine gas means 8NH3 plus 3Cl2 gives 6NH4Cl plus N2 gas, right? 8NH3 ammonia gas when treated with chlorine gas and excess of chlorine gas, it will form ammonium chloride plus nitrogen gas is released here. The next reaction is of hydrazine. Hydrazine is nothing that is N2H4, and this is very important in case of organic chemistry. NH2 NH2, we can write like this, NH2 NH2. Okay, and formation of hydrazine, how can we form? So ammonium chloride when treated with sodium nitrite, right? What is that? NaNO2, right? Sodium nitrite. So NaNO2 plus 2NaOH, it will form N2H4, which is hydrazine plus NaCl sodium chloride plus 2H2 plus 2H2O. Next is oxidation by hydrogen peroxide. Hydrogen peroxide is nothing that is H2O2, right? Peroxide means there is a peroxide linkage like this. Okay, and this is hydrogen, this is hydrogen. Okay, this is hydrogen peroxide. Hydrogen peroxide, so N2H4 reacts with hydrogen peroxide, which is H2O2. It will give N2 plus 4H2. That means nitrogen gas plus water. Nitrogen gas plus water. Next, nitric acid. Nitric acid is a strong oxidizing agent. Nitric acid is a strong oxidizing agent. How can we form nitric acid? So when ammonia is reacted with what? Oxygen, it will form 4NO plus 6H2O, right? And which further form 2HNO3 plus 2NO2 plus 4H2. So 4NH3 plus 5O2 gives 4NO plus 6H2, and which further form what? 2HNO3 plus 2NO2 plus 4H2. Reaction with metals. So what? I told you already, HNO3 is a strong oxidizing agent. So when HNO3 reacts with iron, so it will form FeNO3 whole twice plus 4H2O plus 2NO. 4H2O plus 2NO. So 3HNO3 plus 8Fe gives 3 FeNO3 whole twice plus 4H2O plus 2 NO gas. Next one is reaction with bases. This is an acid, this is a base. So what will happen? Whenever any acid react with a base, it will form salt and water. It will form salt and water. And the salt type, that means acidic salt, basic salt or neutral salt, depends on the types of acid, that means strength of acid or base. Okay, salt plus water. So you can see HNO3 is an acid. We are treating HNO3 with NaOH, which is a base. So you can say simply HNO3, and acid plus base gives salt, which is NaNO3, sodium nitrate, plus water, H2. Like, you can balance this equation. That is very simple. You can see HNO3 plus NaOH gives NaNO3 aqueous plus H2O liquid. Next is phosphorus pentachloride, that means PCl5. PCl5, you know very well, according to VBT, the shape, according to Vesper theory, the shape of phosphorus pentachloride will be what? The valence and electron pair repulsion theory, the shape of phosphorus pentachloride will be TBP, trigonal bipyramidal, and the three chlorine atoms are present at what? Equatorial positions, but 2 chlorine are present at axial position, and the axial bonds are lengthier as compared to equatorial due to repulsion, right? So formation, so you can see PCl3 plus Cl2 gives PCl5, and if you are heating PCl5, again it will provide PCl3 and Cl2. Similarly, reaction with water, when PCl5 is treated with water, so it means PCl5 plus 4H2O, it will provide S3PO4, which is an acid, and plus 5HCl, plus 5HCl, which is also an acid. So this is all about the phosphorus pentachloride. Next one is phosphine, which is PS3. As I told you already, ammonia is NH3, phosphine is PS3. Formation, when you can see Ca3PO2 is treated with 6H2O, so Ca3P2, not PO2, Ca3P2 only, Ca3P2 and plus 6H2O. So phosphorus is here P3 negative, okay, phosphide. It is phosphide because calcium 2 positive, phosphorus 3 negative. So you can write 2 and 3 and then you can cross multiply. You will get Ca3P2. Okay, this is very basic thing. Okay, plus 6H2O gives calcium hydroxide plus 2PS3 plus phosphine 2PS3. So this is prepared, this is formed. Next one is reaction with oxygen. So 4PS3 plus 8O2 gives P4O10, right, plus 6H2. This is the reaction with oxygen, reaction of phosphine with the oxygen. So again I am repeating, phosphine when treated with oxygen, it will form P4O10. It will form P4O10 plus 6H2. The next one is unique behavior of the nitrogen element in its group. You know very well anomalous behavior, right, of the second group elements. That means the first element of every group shows a unique behavior, shows a different behavior from the respective other members, right, of that group. So nitrogen positioned at the top of group 15 because nitrogen, phosphorus, arsenic, antimony and bismuth and so on, like this. So nitrogen exists at the top of the group 15 in the periodic table, right hand side, exhibit unique behavior compared to other element in its group. What is the reason behind this? We will discuss that. Other elements like phosphorus, arsenic, antimony and bismuth. The uniqueness is attributed to a combination of its electronic structure, size and electronegativity. Nitrogen has a particular electronic structure, size and electronegativity is high as compared to other elements. What could be the reason behind this? You can see here. First point is electronic configuration and bonding. You know very well, nitrogen has the electronic configuration, atomic number is 7. So electronic configuration will be 1s2, 2s2, 2p3. That means the last shell is 2s, 2 electrons are there, and 2p. 1, 2, 3 electrons are there, 1, 2 and 3. This is 2p. Its ability to form a triple bond by sharing 3 pairs of electron as in N2 is unique in its group, right, is very unique because nitrogen phosphorus will form P4 but single bonds like this, right. So nitrogen can form N triple bond N. This is very unique, in its group. The triple bond is extremely strong because this is triple bond, and that's why nitrogen is very stable molecule. That means it is very inert in nature. You know, in chips packets nitrogen gas is filled, right, and it is used to stop oxidation. It is like a what, antioxidant. Okay, that's about the nitrogen. Let's move to the second point, size and electronegativity. Nitrogen is the smallest and most electronegative element in its group. It has small size and it is the most electronegative element. Its small size leads to a high electron density. Size is small, so around this nitrogen atom, the electron density is high. The electron density is high, right? In this nitrogen atom, electron density is very high, right, contributing to a strong interatomic interactions. The high electronegativity allows it to form strong hydrogen bonds when it is a part of ammonia, right? So it is forming a strong hydrogen bond. So in case of ammonia, it will form strong H bonds, right? Strong hydrogen bonds. Okay, you know very well about hydrogen bonding, intramolecular or intermolecular hydrogen bonding, or other nitrogen containing compounds, right? Let's move to the next, oxidation state. Nitrogen shows a wide range of oxidation state from -3, right? You can see as in NS3. What is that? You can see in ammonia, this is what, plus -3 oxidation state to NO3 +5. Okay, -3 to +5. One thing I want to tell you, one thing I want to tell you here, in ammonia, nitrogen oxidation state is what? In ammonia, nitrogen oxidation state is -3. Okay, in ammonia, nitrogen oxidation state is -3. I want to show you here again in reaction part. Okay, so ammonia, this is a what? NS3. Ammonia is NS3, PS3 is phosphine, right? So you can see here in ammonia, nitrogen oxidation state is what? -3. Okay, nitrogen oxidation state is what? -3, not +3. Okay, this is -3, not +3. I hope this is clear. So let's move to the next point that we are discussing. Whatever we are discussing, so we are discussing what? Electronic configuration and bonding we have discussed, size and electronegativity we have discussed, and we are discussing oxidation state. So -3 as in NS3, 2 + 5 as in NO3 negative. However, unlike heavier elements in its group, nitrogen rarely exhibit positive oxidation state due to the high energy required to remove its 2p electrons, right? Because high energy is required to remove 2p electrons, that's why nitrogen rarely exhibit positive oxidation state. Let's move to the next, catenary formation. Catenary means like chains. Okay, so unlike its heavier congeners, a nitrogen does not form catenated compounds, compounds containing chains of the same elements like P4, right? Nitrogen, phosphorus, to any significant extent. This is due to the relative weakness, because nitrogen single bond is weak, right? Nitrogen single bond is weak as compared to other single bonds like PP, that means phosphorus, that means arsenic, and SB bonds. Okay, this is about the catenary formation. Next is inability to form d pi p pi bonds. D pi p pi bonds is very interesting because nitrogen has no d orbital, so nitrogen lacks d orbitals in its valence shell, so it cannot form d pi p pi bonds, which are seen in heavier elements like phosphorus and arsenic and in their higher oxidation state. That's all about the d pi p pi bonds. Next is diatomic nature. Nitrogen is diatomic in nature, right? You you can see here, you never see like N3, N4, N5 like this. Okay, because it is diatomic in nature. It exists as a diatomic molecule, which is N2, which is inert in nature, which is not the case with the rest of its group, while other elements generally exist in polyatomic forms or allotropes like P4, you know very well. Okay, let's move to the next point, role in biological systems. Nitrogen is very essential for life, being a key component, right, of amino acids, right? Amino acids gives proteins, right? So proteins are polymer of amino acids, right? And nucleic acids, right? Nucleic acids like DNA, in DNA, RNA, nucleic acids are there. So that's very interesting point. So this biological significance is not mirrored to the same extent by other elements in the group. Let's move to the group 16 elements. So group 15 we have discussed, and I hope you are very much clear about the group 15 elements. Now we are going to discuss group 16 elements. Group 16 elements in the periodic table, you can see here, if I am going to discuss the periodic table, this is like a periodic table, and here is the group 13, here is group 14, here is group 15, here is group 16, here is group 17, here is group 18. In group 16, oxygen, sulfur, selenium, tellurium and polonium, and one more radioactive element. Okay, so you can see top to bottom, if you are moving, size will increase, left to right size will decrease, you know very well, right? Size will decrease due to increase in jet effective. Okay, and top to bottom, if you are going, so ionization energy increases or decreases, indefinitely decreases. Okay, definitely decreases because size increases, and the ionization enthalpy is inversely related to size. So let's discuss these important point. But first of all, let's see the electronic configuration, which is the all over electronic configuration of each and every elements. And if I want to write the general electronic configuration, which is ns2 np4, you can see 2s2 2p4, you can see 3s2 3p4, 4s2 4p4, etc. You can see oxygen atomic number is 8, sulfur is 16, selenium is 34, tellurium is 52, polonium 84. So you can see the electronic configuration of group 16 elements, each and every elements I can say. Now you can see electronic configuration, oxidation state and reactivity. Electronic configuration, general electronic configuration, this is the general electronic configuration. The general electronic configuration is ns2 np4. Oxidation state, it can show from -2 to +6, it can show -2 to +6. Okay, that means it can accept two electrons, as well as it can lose 6 electrons, so -2 to +6. Reactivity, oxygen is highly reactive, while other elements in the family show decreasing reactivity. So reactivity in this case decreases to when you are moving top to bottom. Now let's move to the electronegativity. Oxygen electronegativity decreases down the group, we know very well. So oxygen is more electronegative as compared to other elements. Ionization energy decreases down the group, so oxygen has more ionization energy as compared to the other elements. Atomic radius increases down the group because size increases, jet effective also increases, but due to the addition of new cells, size increases and atomic radius also increases. Let's move to the atomic size. As I told you already, atomic radius increases, so atomic size increases top to bottom in a particular group. What about melting and boiling point? Melting and boiling point also increases because mass increases, right? Density, if mass increases, density formula is mass by volume. So density is inversely related to volume and directly related to mass. So if mass increases, density also increases top to bottom in a particular group. Now I want to go with the physical trends. Physical trends, like you can see electronegativity and ionization energy, we are discussing physical trends. Okay, electronegativity, you know very well. If electronegativity is like a tendency to attract the shared pair of electrons toward itself. If you are moving left to right in a particular period, in periodic table, you can see electronegativity will decrease due to the increase in z effective, right? Due to the increase in electronegativity will increase due to the increase in z effective. That means the what I can say, that means the nucleus attraction power will increase. That means the nucleus hold will increase towards the outermost shell electrons, right? And ionization energy, and electronegativity, one more point. Electronegativity, if you are moving top to bottom in a particular group, size will increase. If size increases, electronegativity will decrease. And ionization energy, if size will increase, electronegativity will decrease. And same, if size will increase, that means electronegativity will decrease, and the hold of the nucleus to the last shell electron is decreased. And if hold is less, definitely it is easy to remove that particular outermost shell electron, so ionization energy is less. So ionization energy decreases as size increases top to bottom in a particular group. Let's move to some reaction part of group 16 elements. You can see reaction with oxygen, with like sulfur, right? You know, oxygen, sulfur, selenium, tellurium and polonium. This is the group 16 element. These are the group 16 elements, and reaction with oxygen, they form oxides like carbon monoxide, carbon dioxide, sulfur trioxide, selenium dioxide, selenium trioxide, etc. Reaction with hydrogen, separately they will form hydrides like H2O, H2S, H2SC, etc. Reaction with halogens, like they form halides like Cl2O, Cl2O3, Cl2O5, etc. Right, etc. I hope reaction with oxygen, hydrogen and halogens are clear. Let's move to reaction with metals. So with metals, they will form metal oxides like MgO and PbO. Reaction with acids, they form oxy acids like H2SO4, like H2SCO4. This is all about the reaction part. Now let's discuss some important reactions of the group 16 elements. You can see first is oxygen. So reaction with hydrogen. Oxygen can react with hydrogen like 2H2 plus O2 gives 2H2O. This is a combustion reaction. Okay. Reaction with metals. So when metal is treated with oxygen, you can see sodium is highly reactive metal. So 2Na plus O2 gives 2Na2O. This is the formation of metal oxide. Similarly, potassium oxide can be formed. Then 4Al plus 3O2 gives 2Al2O3. This is the formation of metal oxide. That means aluminum oxide. Let's move to the reaction with non-metals. Right? They can react with non-metals as well, like carbon. C plus O2 gives CO2. Formation of carbon dioxide. S plus O2 gives SO2. Formation of sulfur dioxide. Now you can move to the next one, sulfur. Reaction with oxygen. Sulfur can react with oxygen. So S plus O2 gives SO2. 2S plus 3O2 gives 2SO3. That means formation of sulfur dioxide, sulfur trioxide, etc. Reaction with metals. Copper when treated with sulfur. You know, in the lower grades we have covered this experiment, like when copper, when iron fillings, right? Iron filings are treated with are mixed with sulfur powder and then heated. Then you will get iron sulfide, right? Which is FeS. This is the formation of iron sulfide. Fe plus S gives FeS. Cu plus S gives copper sulfide, which is CuS. Okay. Let's move to the next reaction with hydrogen. So sulfur can react with hydrogen. It can form H2S gas, right? And H2S gas has rotten egg smell, right? H2S gas has rotten egg smell. So this is the formation of hydrogen sulfide. I want to go with selenium. Selenium, like reaction with oxygen. Reaction with oxygen, so selenium will form selenium oxide. Similarly, selenium can react with 2O2. It can form SCO3. So with the limited amount of action, it will form selenium oxide. With excess, it will form SCO3, which is selenium trioxide, right? Reaction with metals. Reaction with metals, you can see selenium when treated with the sodium metal, it will form Na2Se, which is the formation of sodium selenide. And similarly, Sc plus 2Ag, which is the formation of silver selenide, right? It will form Ag2Sc, right? Similarly, K2Sc can be formed. Okay, I hope this is clear. This is very interesting. This is the reaction of, these are the reactions of selenium. Now, reaction with hydrogen, you can see when Sc is treated with H2. Similar like H2O, similar like H2S, it can form H2SC, it can form H2SC, which is the formation of hydrogen selenide. This is water, this is hydrogen sulfide, this is hydrogen, this is hydrogen selenide. Okay, let's move to the next, tellurium. Okay, what are the group 16 elements? Oxygen, sulfur, selenium, tellurium and polonium. So we are discussing tellurium right now. Te is the symbol. When tellurium is treated with what? Oxygen, right? So you can see sulfur is treated with SO2 and SO3, selenium SCO2 and SCO3, tellurium TeO2 and TeO3, right? Same formation of tellurium dioxide, and with the 2O2 it can form TeO3, formation of tellurium trioxide. Reaction with metals. So Te plus 2Na Te plus 2Na gives sodium, you can say telluride. Similarly, silver telluride, right? So Te plus 2Na gives Na2Te and Te plus 2Ag gives Ag2Te. So formation of sodium telluride and formation of silver telluride you can see here. I hope this is clear. Similarly, reaction with hydrogen you can see. So so in reaction with hydrogen you can see when tellurium, which is a oxygen family element, is treated with hydrogen. So Te plus H2, oxygen, sulfur, selenium, tellurium, polonium, right? So when tellurium is treated with hydrogen, it can form H2Te, which is the formation of hydrogen telluride. Very simple. Like H2O, like H2S, like H2Se, like H2Te. Similarly, you can form group 17 elements. So in group 17 elements, we are going to discuss halogens. Halogens, first of all, let's see the electronic configuration. The general electronic configuration of group 17 elements will be NH2NP5. NH2 NH2NP5. Fluorine, chlorine, bromine, iodine and astenine. Fluorine atomic number 9, chlorine 17, bromine 35, iodine 53, astenine 85. You can see 2s2 2p5, 3s2 3p5, 4s2 4p5 and so on. So this is the electronic configuration of group 17 and in this, first of all, I want to discuss electronic configuration, oxidation state and reactivity. Electronic configuration general is NH2NP5. So it can accept 1 electrons, right? And it can lose 7 electrons. So -1 to +7 it can go. It can the variation of oxidation state is in the range of -1 to +7. Reactivity increases downwards in a particular group. If you are moving top to bottom in halogens, fluorine to astenine, so reactivity will increase. Let's go to the electronegativity. As I told you already, it is a tendency and it decreases. It what I can say, electronegativity will decreases, electronegativity will decreases down the group, electronegativity will decreases down the group, because left to right across a period, if you are moving, electronegativity will increase. But fluorine is the most electronegative element. If you are moving fluorine, chlorine, bromine and iodine, so what happens? Fluorine, chlorine, bromine and iodine, so electronegativity will decrease, not increase. Okay, electronegativity will decrease top to bottom in a group. Ionization energy increases down the group, ionization energy also decreases down the group, ionization energy decreases down the group, because if you are moving top to bottom in a particular group, due to the increase in size, it is easy to remove that last shell electron from its outermost shell, right? So ionization energy will decrease, right? Left to right, due to the increase in Z effective, that means decrease in size, ionization energy will increase. But top to bottom, due to the increase in size, ionization energy will decrease. As we know very well, ionization energy is inversely related to size. So top to bottom, definitely size will increase, so ionization energy will decrease. Atomic radius, size increases, so top to bottom down the group, atomic radius increases, atomic radius increases. Top to bottom down the group, atomic radius increase, not decrease. Okay, so what you can do, you can write this order for period, not for group. Okay, you can write this order for period, not for group. Increases across a period, and the same ionization energy increases left to right across a period. Atomic radii decreases across a period left to right, but top to bottom atomic radius increases. Similarly, atomic size increases. Top to bottom in a particular group, atomic size increases. Melting and boiling point also increases down the group, and density increases down the group, because density formula is mass by volume, right? If mass increases, density also increases. Let's move to the next, electronegativity and ionization energy. Electronegativity and ionization energy increases down the group, right? Electronegativity decreases down the group, and ionization energy also decreases down the group, because size increases, so ionization energy becomes low and low and low. That means ionization energy decreases down the group. Okay, decreases. We have discussed these points, we have discussed this point as well. Okay, okay, let's move to the next, reactions. First is reaction with metals. It form metal halides, it form metal halides like NaCl, MgCl2, CaCl2. CaCl2 is right, CaCl2 you can write, right? CaF2 you can write, etc. Okay, MgBr2 you can write. Reaction with hydrogen, so forms hydrogen halides with metal, metal halides with hydrogen, hydrogen halides like HCl, HBr. Okay, then reaction with oxygen, so it forms oxo acids like HClO4, HClO3, BrO3, etc. Then the next point is here, fourth, displacement reaction. So halogens can displace each other from solutions of their salts. For example, if you are passing chlorine gas from NaBr solution, right, Cl2 plus 2 NaBr, it will form, it can replace bromine, and it can form 2 NaCl plus Br2. That's very simple. Similarly, reaction with alkenes, so it form halogenated organic compounds. So when chlorine is reacted with what? CS2 double bond CS2, which is an alkene, which is named as ethene. So you will understand a clear idea about this reaction in the organic chemistry. So Cl2 plus CS2 double bond CS2 in presence of like a solvent like CCl4, it will form Cl. Cl, CS2, CS2, Cl. Okay, so this is 1 comma 2 dichloroethane. This is 1 comma 2 dichloro and eth plus n, ethane, dichloroethane. Okay, next one is unique behavior of the oxygen element in its group. What about the unique behavior? Oxygen located at the top of group 16, you know very well. First is oxygen, then sulfur, then selenium, then tellurium, then polonium, we know very well. Okay, in the periodic table, it exhibit unique behavior compared to other elements in the group like sulfur, selenium, tellurium, and polonium. Okay, the distinct behavior arises from its electronic structure, size, electronegativity, and other physical properties, right? So some key aspects you can see here. First is electronic configuration. Oxygen atomic number is 8. Electronic configuration will be 1s2, 2s2, 2p4. right? So its ability to form double bonds as in O2 is a notable feature. It's very notable feature. It can form O double bond O in a molecular oxygen, is significantly strong but not as strong as N triple bond N, right? Triple bond, you can understand like triple bond is more strong as compared to double bond, right? Okay, so you can see N2 is more inert. Okay, let's move to the next, size and electronegativity. Oxygen is the smallest and most electronegative element in its group. Its small size leads to high electron density, very high electron density around the nucleus, right? Due to the small size, the electron density becomes around the becomes around the so in this case, high electron density is here. Okay, and high electron density around the nucleus and making it high electronegative. Due to this reason, this is highly electronegative, and in its group, okay, in its group, this high electronegativity allows oxygen to form strong hydrogen bonds, which is crucial in water and vital for its unique properties, right? In water, hydrogen bonding is here, right? In water, hydrogen bonding is there, right? So hydrogen bond can be formed by fluorine, oxygen and nitrogen, right? Most electronegative element. Okay, let's move to the next, oxidation state. Oxygen primarily exhibit a -2 oxidation state. It wants to accept electron to complete its octet. Unlike its heavier congeners, which show multiple positive oxidation states, the positive oxidation states are rarely seen in oxygen due to its high electronegativity. Due to its high electronegativity. Next is diatomic nature. Oxygen exists as O2. It is the most stable form. Oxygen exists as a diatomic molecule. It can exist as O3 as well, right? Which is ozone, and that is a unique feature in its group. Absence of d orbital, definitely oxygen belongs to second period. So oxygen atomic number is 8, 1s2, 2s2, 2p4 is the electronic configuration. So it belongs to second period. That means no third period is here. So if n value is 2, so definitely d value for d, l value will be 2, and n and l never be equal. L is always smaller than n. So oxygen lacks d orbital in its valence shell, which limits its ability to expand its octet. So it cannot expand it octet, right? And form compounds with oxidation state higher than +2, a feature observed in heavier elements like sulfur and selenium, right? So that's all about the due to the absence of d orbital. Now the next point is here, role in biological systems. Oxygen is essential for a life as component of water. First of all, water is life, right? And as a key player in cellular respiration. If we are inhaling oxygen and exhaling carbon dioxide, right? So in both cases you can see oxygen formula is O2 and carbon dioxide formula is CO2. In both cases you can see oxygen atom is very crucial. Okay, and the next point is very simple, allotropes. Oxygen has a notable allotrope, which is ozone, which plays a very crucial role, very important role in absorbing harmful UV rays, ultraviolet radiations in the earth atmosphere, right? This allotrope is less common in other atoms of group 16 elements. Next is reactivity and formation of oxides. Reactivity and formation of oxide, you can understand like oxygen is highly reactive and forms oxides clearly. Like sodium can react with oxygen, it can form sodium oxide, potassium oxide, silver oxide, etc. Nearly all other elements, these oxides are often fundamental to various chemical processes including like corrosion, combustion and cellular respiration. Okay, next, important reactions of the group 17 elements. Some important reactions are there, like for fluorine. Fluorine can react with the metal to form metal fluoride. So 2F2 plus 2Na gives 2NaF. 2F2 plus 2Ka gives 2Kf. Reacts with non-metals to form covalent compounds like F2 plus Cl2 gives 2ClF. This is intrahalogen compounds. This is intrahalogen or interhalogen. This is interhalogen. That means two different halogens are there. This is interhalogen compounds 2ClF. Chlorine can react with metal, so it can form same metal chloride, that means 2NaCl. Reacts with hydrogen, it can form hydrogen chloride, that like 2HCl. Reacts with bromine can react with metal, it can form like 2NaBr, which is sodium bromide. Similarly, it can react with hydrogen, it can form hydrogen bromide like 2HBr. Iodine reacts with sodium metal, it can form 2NaI, which is sodium iodide. Similarly, it can react with hydrogen, it can form hydrogen iodide, which is 2I. What is the unique behavior of the fluorine, first element in its group? Fluorine is the first element in its group, right? I am writing again, fluorine, then chlorine, then bromine, then iodine, then acetylene. Okay, top to bottom, atomic size increases, ionization energy decreases, top to bottom. electronegativity decreases, right? These are some points you have to be keep in your mind always. So fluorine situated at the top of the group 17 in the periodic table exhibit unique behavior, right? As I told you already, second period element shows some uniqueness, right? Show some anomalous behavior due to some reasons, due to their small size, due to high electronegativity of others elements, right, of other elements of their respective groups. So they exhibit unique behavior compared to other halogens like chlorine, bromine, iodine, and acetylene. The behavior is due to its small size, high electronegativity, and other physical and chemical properties. Electronegativity, ELECTRO, electronegativity and other physical and chemical properties, here are the key aspects of fluorine unique behavior. So high electronegativity, you can see here fluorine is the most electronegative element in the periodic table. This high electronegativity enables it to attract electrons and more effectively than any other element, influencing its chemical reaction and bond formation. So fluorine is the, as I told you already, fluorine is the most electronegative element in its periodic table, right? Here is the fluorine, right? So you can see fluorine in group 17, and this is the most what I can say, most electronegative element in the periodic table, right? So due to this most electronegative feature na, it due to its high electronegativity, it has a tendency to attract the electrons more effectively as compared to any other element, right? Not in its respective group, in the entire periodic table, you can say, and that's influence its chemical reaction and bond formation as well. It has a very small size and atomic radius. Due to the small size, it has high electronegativity, right? So fluorine has a high electron density and a strong effective nuclear charge. If it is at a strong effective nuclear charge, so immediately it can attract the electron, right? So this contributes to its high reactivity and aggressiveness, right? It's like aggressive, it becomes very aggressive whenever suppose this is fluorine, and due to its high electronegativity na, suppose if an electron is here, so it can accept this electron with more power and more effectively, right? So it's like a aggressive for this electron in chemical reaction. Now the next part is here. So reactivity, fluorine is extremely reactive, right? More so than any other halogens, right? For chlorine, bromine, iodine, they are less reactive than fluorine, right? It can react with almost all other elements including noble gases as well, right? It can form compounds with noble gases like xenon compounds of fluorine, xenon fluorides can exist, right? Okay. So under certain conditions, this reactivity is so high that it can hazardous, making fluorine difficult to handle safely as well. Now the next point is formation of strong bonds. The bonds formed by the fluorine, for example, CF bond, carbon fluorine bonds, are among the strongest single bonds formed with carbon. This is due to its high electronegativity and small atomic size. That means the overlapping will take place very clearly, and due to its high electronegativity, the bonds become strong, right? And due to its small atomic size, the overlapping will be, the region of overlapping will be more. Next is oxidizing ability. That means it can oxidize others and itself get reduced. Oxidize others means it can accept electrons very quickly, right? That means electron acceptor. That means other elements can lose electrons whenever fluorine is here, okay? So fluorine is the strongest oxidizing agents among the halogens. It can oxidize substances that chlorine, bromine, and iodine cannot, right? So it can oxidize those substances, and those substances cannot be oxidized by chlorine, bromine, and iodine. That means other halogens, okay? So it has an oxidizing ability. That means it is acting as an oxidizing agent, strong oxidizing agents. It means if it is a strong oxidizing agent, so itself undergoes reduction, and it can oxidize the other one, okay? I hope this is clear. The next one is unique chemistry with hydrogen. So hydrogen fluoride, due to hydrogen bonding, it can exist hydrogen bonding as well. So hydrogen fluoride exhibit properties not seen with any other hydrogen halides. For example, HF forms a relatively strong H bonding, strong hydrogen bonds, leading to a higher boiling point compared to other hydrogen halides. If you are comparing HF, HCl, HBr na, if you are comparing these, so definitely Hi, so definitely HF has more boiling point as compared to the other one, right? More boiling point as compared to the other hydrogen halides due to the presence of strong hydrogen bonding. Let's move to the next, non-existence of higher oxidation state. Unlike other halogens, fluorine only exhibit a -1 oxidation state in its compound due to its high electronegativity, right? And it does not show positive oxidation state generally because it lacks d orbitals to expand its valence shell. That's the point about fluorine. Next, compounds with noble gases. Fluorine is one of a few elements that can form compounds with noble gases like xenon, fluorides like XeF4, like XeO3, right, etc. Because xenon can form compounds because of some reasons, right? So it provides a particular amount of energy, right, which xenon required to remove their electrons. So let's move to the next point. Role in organic chemistry. Fluorine unique reactivity has leads to its widespread use in pharmaceuticals and agrochemicals, right, industry. The introduction of fluorine into organic compounds often significantly alters their properties and activities. So this is the interesting part about the fluorine. Next is impact on physical properties. You can see here the presence of fluorine often dramatically changes the properties of compounds, such as like increasing thermal stability and resistance to solvent. Okay, so this is about the fluorine. So what I can say, fluorine is the most electronegative element. Fluorine is the most electronegative elements. Let's move to the next and interesting point. The next interesting point is about introduction of noble gases. What are these noble gases? Noble, like inert gases, that means not reactive, that means not reactive, right? So you can see first of all the electronic configuration of group 18, which are noble gases, right? What are noble gases? So noble gases are not reactive gases, that means inert gases. And you can see the electronic configuration. General electronic configuration will be NH2NP4, right? NH2NP4 or 6, NH2NP6, okay, not 4. 4 is for group 18, okay, group 18. 4 is for group 16, which is oxygen family, and this one is for group 18, which is halogens, that which is halogens are group 17, and this one is group 18, which is noble gases. Okay, so helium, neon, argon, krypton, xenon, and radon. You can see 1s2, then you can see 2s2 2p6, 3s2 3p6, 4s2 4p6, and so on, right? This is about the electronic configuration of group 18 elements. Let's introduce noble gases. Noble gases are a group of elements that includes helium, neon, argon, krypton, xenon, and radon. They are called noble gases because they are generally what? Generally unreactive. They are not reactive, as I told you already multiple times, and they do not readily form compounds, right? They do not readily form compounds. This is due to their stable electronic configuration. Their octet is complete. Their octet is complete. If their octet is complete, definitely they are stable. They are stable. They have less energy, right? So low reactivity. What is the reason for low reactivity? Noble gases have full valence electron shells. That means their octet is complete, which makes them stable and unreactive, and they rarely form compounds with other elements. Definitely they are unreactive. Now they are low reactive. I told you already. The low reactivity is due to the fact that they have a complete set of valence electrons. They have a complete set of valence electrons. That means if I am talking for fluorine, fluorine atomic number is 9, so 1s2, 2s2, 2p, 5. So one electron is left here. But if I am comparing like neon, so neon atomic number is 10, so electronic configuration will be 1s2, 2s2, 2p6. That means it is fully packed. That means it is a fully packed. It is fully packed. So this is all about the low reactivity. Next is important reactions of the group 18 elements noble gases, right? So let's discuss some important reactions. Like you can see for xenon, right? Helium, neon, argon, krypton, xenon. So some important reactions for xenon, because all halogens, all noble gases cannot form compounds, right? So some noble gases, some exceptions are there, like xenon fluorides. You can see Xe plus F2 gives XeF2. Similarly, higher fluorides will be XeF4 and XeF6. Okay, XeF4 and XeF6 can exist. Xenon oxides like Xe plus O2 gives XeO3, right? Similarly, you can see this is xenon trioxide. So let's move to the krypton. Krypton can react with fluorine. That means Kr plus F2, it can form krypton difluoride. Okay, and limited chemical compounds compared to xenon. So krypton has very limited chemical compounds. Okay, next is radon. Radon fluoride's reactivity similar to xenon, and radioactive nature limits practical application. So radon is like radioactive in nature. Other noble gases like helium, neon, and argon. Helium, neon, argon extremely low reactivity and no stable compounds known, right? No stable like HeF2, HeF3, no stable compounds like known so far. So let's move to the exception part, xenon and krypton. So xenon and krypton are exceptions to the general rule of noble gas reactivity. That means noble gas are not reactive, they are unreactive, they are less reactive. But xenon and krypton can form compounds. Like it is written, like noble gases are not reactive. That means they cannot form compounds. But xenon and krypton can form compounds. They can form compounds under certain particular conditions, such as high pressure, high temperature, etc. Example, like you can see xenon PTF6. Okay, xenon hexafluoroplatinate. Okay, this is PTF6 negative, and xenon is attached here. PTF6 is negative, and krypton difluoride like KrF2. Let's move to the next uses of noble gases. Noble gases have various practical uses due to their unique properties. Right, helium is used in balloons, airships, and as a coolant in certain applications. Right, you have seen helium is used in balloons, and balloon will whenever a balloon is filled with helium gas, na, you can see balloon will go upwards or not, right? So that's the point. Okay, neon is used in science and lighting. Okay, let's move to the next. Argon is used in light bulbs and such as in, like as an inert gas in welding part. In light bulbs, what happened, argon gas is filled because argon is less reactive or extremely low reactive. Okay, krypton and xenon are used in lighting and as insulating gases in windows as well. So some exceptions, some compounds are formed by krypton and xenon, but other halogens are not forming compounds. Let's move to some important question for JEE exams, right? So let's see the relevancy. You can see here which one has the highest boiling point. As I told you already, you can see these all are noble gases. These all are noble gases. You know very well, I am just summarizing some properties. You can see this is the periodic table, and if you are moving left to right across a period, so electronegativity will increase, size will decrease. Electronegativity will increase, size will decrease, atomic radius will decrease, ionization energy will increase, again I am repeating, as you are moving left to right across a period, electronegativity increases, size decreases due to increase in Z effective. So Z effective increases, right? Z effective increases, electronegativity will increase, size decrease, atomic radius decrease, and ionization energy increase due to the decrease in size. That means the hold of the nucleus, that means the attraction between electrostatic attraction between the nucleus and the last shell electrons are more, right? Are high. Okay, that's. But if you are moving top to bottom, Z effective increases. Z effective definitely increases. Electronegativity, I can't say Z effective increases, I can say, or you can say Z effective increase, right? So because number of protons and electrons both are increasing, right? If you are moving top to bottom, electronegativity will increase or decrease. Electronegativity will decrease. Size increase due to the addition of new cell. Size increase, electronegativity will decrease. Ionization energy, if size will increase, that means the hold of the nucleus towards the last cell electrons, right, which we want to remove, is less. If it is decreasing, definitely it is easy to remove and ionization energy becomes low. So size increases, ionization energy decreases. Ionization energy decreases as well as atomic radius decreases. These are some basic points. So you can see in this question we have given helium, neon, argon, krypton, xenon, radon, right? So these are the noble gases. If you are moving top to bottom, right, top to bottom down a group, what happens, molecular mass increases, so interactions will increase. So you can see the reason of the answer of this question is xenon, and the reason is here. As we move down the group of noble gases, molecular mass increases, by which dipole produced, right, they will produce a momentary dipole, so the dipole produced for a movement, and hence London forces increases. If London forces increases from helium to xenon, right, more bigger the dipole, more bigger the momentary dipole, more will be the attraction type. Okay, so London force will be more, and London forces increases, so definitely melting point, boiling point will increase. Therefore more amount of energy is required to break these forces, and hence boiling point of xenon is more, right? So xenon has the highest boiling point. Let's move to the next question. The molecule having the smallest bond angle, you know very well, a nitrogen, phosphorus, arsenic, antimony, and bismuth, right? So as you are moving top to bottom, size will increase, electronegativity decrease, right? Ionization energy decrease, etc. So the smallest bond angle is question. You can see NCl3, ASCl3, SbCl3 and PCl3. The shapes are same. You can see the shape will be like pyramidal shape for all, right? It's like this, okay? But it totally depends on the electronegativity. If electronegativity is increasing, so the pairs of like lone pairs or bond pairs are more close towards the center atom, which is like nitrogen in case of NCl3, in case of ASCl3, which is AS, right? Arsenic. So which is what I can say, if more electronegative, if the center atom is a more electronegative atom, so the lone pairs or bond pairs are more close towards the center atom, and they will feel more repulsion, they will feel more repulsion. So in this case you can see the solution here. The answer is SbCl3 definitely. You can see nitrogen, phosphorus, arsenic and antimony group 15 and valence electrons are 5, right, in each case. So MCl3 has a sp3 hybridized M element with one lone pair, right? You can see M is this: nitrogen, phosphorus, arsenic and antimony. These are generally represented by M. So you can see in each case like NCl3, PCl3, ASCl3, SbCl3, they are sp3 hybridized. That means they have tetrahedral type geometry, but the shape is what? Trigonal pyramidal. Shape is trigonal pyramidal. So lone pair and bond pair repulsions decreases bond angle. If lone pair, like you know very well, lone pair repulsions are more than bond lone pair bond pair, then lone pair bond pair, then bond pair bond pair. If these repulsions are what? More, what happens? So here are lone pair bond pair repulsions. So if lone pair and bond pair repulsions are decreases, so they decrease the bond angle. So the bond pair of electrons are much farther away from the central atom in SbCl3, in SbCl3, which is less electronegative, because electronegativity is decreasing as we are moving top to bottom in a particular group, in 15th group, right? Then in that they are in NCl3, in NCl3 they are very close, but in SbCl3 they are farther away from the central atom. Thus lone pair causes even greater distortion in PCl3, ASCl3 and SbCl3, right? Hence bond angle decreases from NCl3. NCl3 has maximum bond angle to SbCl3, and answer will be C. Okay, so the smallest bond angle is present in SbCl3, right? You can say, which is antimony trichloride. Lone pair causes even greater distortion in PCl3, ASCl3 and SbCl3. I hope you are getting this point. This is very interesting. Next question. Among the following oxo acids, you can see these are oxo acids, the correct decreasing order of acidic strength. The correct decreasing order of acidic strength. So in mostly if the question is asking the correct decreasing order of acidic strength, so what you have to check, you have to check, suppose this is acid Ha, so it will release H positive and this will be the conjugate base, right? So you have to check the stability of this conjugate base as well, right? Stability of this conjugate base, stability of conjugate base. More the stability of conjugate base, more acidic, right? The more acidic this acid, okay, the acidic nature of this acid will be more. So more stability of conjugate base, more the acidic nature, more the acidic nature, more the acidic nature, acidic nature. Okay, so let's see the stability. So we have given SClO, SClO2, SClO3, SClO4. Four options are there, right? So you have to check only the stability of what? Stability of conjugate ion. So you can see the solution of this particular question. The answer will be C. How? You can see decreasing order of strength of oxo acids. You can see SClO4, then SClO3, then SClO2, then HOCl. Okay. Negative charge. What is the reason? Negative charge is more delocalized on ClO4 negative, right? You can see here, if negative charge is here, so it will go here due to resonance, then it will go here. Similarly, then it will come back and it will go here like this. So negative charge is getting dispersed more in case of ClO4 negative. If it is getting dispersed more in a case of ClO4 negative, so definitely it is more stable. So ClO4 negative is more stable as compared to other conjugate bases. Then ClO3 is stable, then ClO2 stable, and then ClO negative stable. Okay, this is the least stable in these conjugate bases. This is the least stable. Okay, so negative charge is more delocalized on ClO4 negative due to resonance. Hence ClO4 negative is more stable and less basic. It is less basic means most acidic. More stable, most acidic among these. So we can say that number of oxygen atom around chlorine atom increases as oxidation number of chlorine atom increases, and thus the ability to lose the H positive increases. The ability to lose the H positive increases. I am showing the you can see Cl, what I can say, you can see here Cl double bond O. I am showing the structure of ClO4 negative, double bond O, double bond O, double bond O, and O negative. I am not presenting the what I can say lone pair. So it will go here, then it will go here. Okay, then what will be the next structure? This will be O negative, double bond O, double bond O, double bond O. Then it can come here and it can go here. Then Cl, then double bond O, then similarly double bond O, double bond O. This is O negative and this is double bond O. Then it can go here and it can come here. So you can see the negative charge. So more the number of resonating structures, more will be the stability. You can understand like this. Cl double bond O, then it is O negative, it is double bond O, and it is double bond O. This is for ClO4 negative. Similarly, you can draw for ClO3 negative, ClO2 negative, ClO3 negative, ClO2 negative, and ClO negative, right? ClO negative. If I want to draw for ClO3 negative, so Cl, then double bond O, double bond O, O negative. This is Cl. So it can go here, it can go come here. So Cl double bond O, single bond O negative, double bond O. Then this and this. Then you can see here Cl, single bond O negative, double bond O, and double bond O, like this. So you can draw the structures for rest. Okay, you can draw the structure for rest. So in simple words, we can say stability of conjugate base, the acidity or you can say acidic nature. The acidic nature depends on stability of conjugate base. More the stability of conjugate base, more acidic, because it will release, if the conjugate base is more stable, then it will release the H positive ions very quickly. But if the conjugate base is less stable, then the easiness of release of what I can say H positive ion is less. Okay, that's all about the second. Next question: which of the following statement is incorrect? You have to choose incorrect statements. The stability of hydrides increases from NH3 to BiS3 in group 15 of the periodic table. That means the question is saying that here it is in +3 oxidation state, here it is in -3 oxidation state, and you can see similarly for Bi. So nitrogen cannot form d pi p pi bonds. Single and nitrogen bond is weaker than the single pp bond. So this is correct, we know very well. N2O4 has two resonance structures. So let's see the answer. First, the thermal stability of the hydrides decreases as we go down the group in periodic table for group 15. You can see BiS3 is least stable and NS3 is more stable. You can also see the metal hydride bond dissociation energy or bond energy, right? You can see the values as well. So definitely, as you go down the group in group 15, so what happens? The thermal stability of the hydrides decreases. That means NS3 is more thermally stable as compared to other. Okay. Due to the absence of d orbital, nitrogen cannot form d pi p pi bonding. Thus, it is correct. Okay. The nitrogen bond is weaker than the pp bond. You can see the bond energies as well. N2O4 can form two resonating structures. You can see here the two resonating structures of N2O4. This is N2O4. This is N2O4 and this is the another. So it is also correct. So what should be the right answer? The first D is correct, C is correct, B is correct. So what is the wrong? Wrong is here A. Okay, wrong is here what? A. The stability of hydrides increases from NH3 to BiS3. As we know, a thermal stability is more for NH3 and less for BiS3. You can see the thermal stability is more for what? More for what I can say in simple words. The thermal stability is more for what? NH3 and least for BiS3. So BiS3 is least stable. Let's discuss the next question. Next is which of the following statements regarding sulfur is incorrect? Again, you have to find incorrect statement. So S2 molecule is paramagnetic. Okay. The vapor at 200 degrees Celsius consists mostly of S8 rings. At 600 degrees Celsius, the gas mainly consists of S2 molecules and the oxidation state of sulfur is never less than +4 in its compounds. So you have to always remember the temperatures as well. So you can see the solution part A. That means option A. S2 molecule is paramagnetic due to unpaired electrons is MOs. MOs is a molecular orbital theory you have done, right? So you can draw the molecular orbital theory, but you can see when you will draw the molecular orbital theory of S2 molecules, you will see that there will be unpaired electrons. So due to the presence of unpaired electron, right, what will happen? Due to the presence of unpaired electrons, it will be paramagnetic, right? If number of unpaired electron is not equal to 0, so mu comes out to be not equal to 0. If mu is not equal to 0, definitely it will be paramagnetic, right? And it is blue colored actually, okay, that it is true. The vapor at 200 degrees Celsius consists mostly of S8 rings, right? That is also true, right? It consists mostly of S8 rings. At 600 degrees Celsius, the gas mainly consists S2 molecules. This is also correct, okay? You have to remember the temperatures, again I am repeating, okay? The next part is here, oxidation state of sulfur R. So you can see here, if I'm taking some examples, like you can see some examples of oxidation state are H2S. In H2S, the oxidation state will be, for sulfur I have to mention X, and this is plus 2, then equal to 0, then X comes out to be minus 2, okay. In acid it is 0, right? And in H2O3 negative, you can see it is 2X, then minus 6 equal to minus 2, then it comes out to be X is plus 2. Similarly, in this case X is plus 4, in this case X is plus 4, in this case X comes out to be plus 6. It can go beyond 4 plus 4 as well. Thus the incorrect statement is this, that oxidation state can be less than 4, right? So that is the point here. I hope you are getting this point, so you can understand this question very clearly. Now the next question, which among the following is the most reactive? So Cl2, Br2, I2 and ICl, these options are given. You have to complete this question, okay, as a homework. The solubility order of alkali metal fluoride in water is LiF, RBF, KF and NaF. Very simple, okay. And some other options are given to you. You can go through this question and you can complete this question because you know the concepts, okay. Next, which of the following statement is true? S3PO3 is a stronger acid than H2SO3. In aqueous medium, HF is a stronger acid than HCl. HClO4 is a weaker acid than HClO3. HNO3 is a stronger acid than HNO2. So you have to check the answers according to, you know very well, you can release H positive and then you will get conjugate base and you can check the stability of conjugate base, okay. Consider the following statements. NCl5 does not exist while PCl5 does, right? NCl5 does not exist, so can nitrogen have d orbitals? That will be the hint for this particular question. If nitrogen have d orbitals, it can expand it what, when covalency, right? So both O2 positive and NO are paramagnetic. Very interesting question. Therefore 3 carbon single bonds, O bonds are not equal in carbonate ion. Carbonate ion is CO3 2 negative. So the question is saying that in carbonate ion CO bonds are there, carbon single bond oxygen bonds are there, which are not equal. And next is fourth one. Fourth one is what? Lead prefers to form tetravalent compound. Lead prefers to form tetravalent compounds. That is true or not? That means out of PbCl2 and PbCl4, lead prefers, a statement is saying that lead will prefer PbCl4, not PbCl2. Why? And if it is correct, then you can understand the concepts, and if it is not correct, so you have to choose the answer very clearly, okay. So next question you have to complete as a homework. Which of the following is the wrong statement? O3 molecule is linear, ozone is violet black in solid state, and ozone is diamagnetic gas, and ONCl and ONO negative are isoelectronic or not? Are isoelectronic or not? So you have to choose. Again I am saying wrong statement, so you can complete these question as a homework. So this is all about this today's class. Thank you so much.